going to do a couple of problems to understand how matrix algebra and eventually linear algebra works in general. I'm quite not certain how I'm going to do this because I'm going to try and tailor most of the audience of my videos as much as possible to the IBHL applications and interpretations high school math audience. However, in my opinion, with the ethos that they're going with for applied math, and they're really omitting a lot of theory, I just don't think they do linear algebra justice. Let me just put it to that in that matter. So we'll do what we can, but a lot of simplifications will have to be made along the way. Now let's get right into the problem here. So assume for simplicity, let there exist square invertible matrices of dimensions or dimensions 2 by 2. So 2 rows and 2 columns. We call them T and X. And we know in elementary algebra, with real numbers at least, that if you multiply the sum and difference of 2 real numbers together here, you get the difference of 2 squares, which is this. And if you do a plus b, all quantities squared, get 2 copies multiplied together, you get a squared plus 2ab plus b squared, where a and b are real numbers. So this is how you write in set theory notation. Now expand the above mentioned square matrices, using properties of matrices, and explain why the 2 identities up top do not work. So the key main idea why this doesn't work is that matrix multiplication is not commutative. And I'll kind of have to show this perhaps with some examples or give a proof later on in future, but matrix multiplication is basically a type of operation, non-arithmetic operation, that is very analogous to function composition. And function composition is not commutative. So by that loose argument, it should follow that matrix multiplication is not commutative as well. So yeah, let me put it this way. We can make an analogy with matrix multiplication and function composition. Yeah, let me bullet point these just for clarity. Since function composition is not commutative, it follows that matrix multiplication is also not commutative by analogy. So that's basically a 2 or 3 propositions sentence argument for it. And I can give a quick funky example, but not with numbers, unfortunately, because I'm not good with numbers, as to why function composition is not commutative. The examples I'll be using are 2 general linear functions. So let f of x equals ax plus b, g of x equals cx plus d. Now compose them in different orders. We have f of g of x, which just becomes f of cx plus d. But then the cx plus d here we add into this domain input here for the f of x function. So you just get a times cx plus d plus b. If we do the other way around, g of f of x equals, let's see, g of ax plus b. So that's c of ax plus b plus d. I can do a couple of simplifications here. I'll get acx plus ad plus b. And here I'll get acx plus cb plus d. So although the linear terms match up, the constant numbers do not. And for that reason, function composition is not commutative. We have just given a counterexample in this case, because I could show like that function composition is not commutative for many different kinds of functions, but it suffices to show with these two linear functions that it doesn't work. Okay, and now you just have to trust me. You need to trust me. You need to please trust me. That matrix multiplication is analogous to function composition. Okay, so that's a big takeaway with this. So that was a little bit of an aside, just on fundamentals here, and kind of because I'm spitballing as I'm doing this video. But now let's go and like expand these things here. So we go and expand this properly. T plus x times t minus x. You're really going to have to go and distribute things evenly here. Let's see, I'm always trying to think. Let's see. Yeah, I almost want to... No. Just think of it like term by term. Term by term. Okay, this might be a bit overcomplicating it, but I might even like reduce these into individual components. This we're allowed to do. And then from there we get t squared. Okay, yeah, it's the order. It's the order. Yeah, because tx is not the same thing as xt. Okay, yeah. That's how it works out. Okay, so to multiply this out, this will be t squared. T goes to t squared, t goes to t, so you get t squared first. Then I add plus t times minus x, so the order that you multiply has to matter. And then I add this with x multiplied with t. And then this gets added by x times minus x, being very anal about the order that I'm multiplying things here. In fact, let me just go and, yeah, let me put it like this here. So given this, that's t squared. I can factor out any scalars, -1 here, or a number from here. That's allowed. What I cannot do is rearrange around the orders of the matrices themselves. So if I factor out the scalar -1, that becomes a tx, and then I get an xt here. I can factor out a scalar -1, and I get x times x. I'll leave it like this. Before I square this for it, let me leave as tt. Now this is t squared minus tx plus xt minus x squared. So that is the only thing that can hold in general. And no, we cannot simplify. We cannot simplify this into what was it? Yeah. T squared minus x squared. Because the terms minus tx and xt cannot cancel out with each other. Let's do the same thing again with t plus x squared, which is the same as t plus x times t plus x, and then we'll call this video a wrap. So that's tt plus tx. So I do this, get this t first, and I multiply with this t. Then I add with this product t being multiplied with this x here to get tx. Next I add with the third term. This term x here gets multiplied with this t here. So I get xt. And then finally I get this x here, and I multiply it last with this term x to get xx, which in general just becomes t squared plus tx plus xt plus x squared. And yep, these two matrices are not the same. tx does not equal to xt. So I cannot combine these matrices together by addition. So this can't become 2tx. So yes, this is the proper expansion result that we have for the n. For, I guess it works for any n by n finite dimensional matrix, but for this case we'll consider it 2 by 2. So yes, let me write the key result that we've proven. T plus x times t minus x. Oops, sorry. T minus x equals t squared minus tx plus xt minus x squared. And then finally we have, what was it? T plus x squared equals t plus x, which equals t squared plus tx plus xt. So yeah, if there's anything to take away from this video quickly, and I'll end it with this, is that matrix multiplication is not commutative. And that is why matrix algebra is significantly harder than elementary algebra that you did with real numbers and heck, even complex numbers. Thank you. Hope you enjoyed the video.